So Marcela asked me to share some of the examples from Canada with regard to monitoring disturbances for national scale reporting on greenhouse gas emissions and removals. So what I will do is give you a very quick overview of the National Forest Carbon Monitoring, Accounting and Reporting System that we're using in Canada. I will talk about the way we represent disturbance impacts and give two examples, insects and fires. I'll show you a few results and some conclusions. And it's great that Richard has given the presentation before me because he has explained and reiterated some of the same issues that I spoke about yesterday with regard to carbon dynamics, the direct impact of disturbance, the subsequent recovery. And while we're working with two different models, the principles are very much the same of the two approaches. So like in Mexico, our Ministry of Environment is responsible for the production of the annual greenhouse gas inventories that we submit to the United Nations Framework Convention on Climate Change. And it is the Canadian Forest Service, the team that I'm leading, that develops the greenhouse gas emissions and removals estimates for the forest sector. And we do that with a carbon budget model that we started developing 20 years ago. It is published in this paper in ecological modeling and many others that have been published before and since. And it is a inventory-based tool that allows us to represent the carbon dynamics. It's a generic framework, and that is why it is used in many different countries, including Mexico. Some of the analyses that you saw yesterday that Marcela presented were built with the same framework that I'm describing here. So this is a modeling tool. It is comprised of software and databases. We have users guides, tutorials. We run training workshops. We ran a training workshop here in Mexico a few years ago. The next training workshop will be in February in Quebec. It was just announced yesterday. So if anybody's interested, those opportunities exist. As I mentioned yesterday, because of the United Nations Framework Convention proxy of the managed land, we only report emissions and removals for 230 million hectares of managed forest. That is the darker forest area with boundaries in the north defined by the limits of fire protection, harvesting, and management. To help put things in perspective, this area up here, the Yukon, has about 40,000 inhabitants. This area here has about 40,000 inhabitants. So when we're asked, why are you not suppressing fires? There are no people. So what we're doing with this model, as I explained yesterday, it's a general framework that allows us to represent a wide range of disturbances, natural disturbances, like fires, like insects, and forest management activities like logging, as well as land use changes. As I explained yesterday, changes in climate and atmospheric conditions are dealt with separately. They're not dealt with as disturbances per se. Similar to the discussions we had yesterday, we represent different types of insects. We have defoliating insects that at low levels of defoliation, their primary impact is growth reduction, but if you have repeated defoliation events, you also see tree mortality occurring. And as I indicated yesterday, in the model you can set it up so that stands that were affected by a defoliation in the first year of the simulation, you can then target a second-year defoliation or a third-year defoliation in subsequent years. A second type of insect are bark beetles. They have a different mechanism of killing trees. They tend to kill trees much more rapidly, and they're also represented in these models. So I'll give you one example of the insect, of the bark beetle impact. As you saw in Richard's slides, in Western North America, we're currently experiencing a very large impact, outbreak of mountain pine beetle This is an endemic insect. It's an insect that is native to these regions, but due to a series of circumstances such as past fires in the 1880s, 1920 period, that allowed to naturally regenerate vast areas of pine forests that have been successfully protected against fires, and we had low harvesting rates, allowing now a large cohort of pine beetle hosts to be present in the landscape. And when we combine that with climate changes such as the warmer summers that have allowed higher survival, higher reproduction, warmer winters that allowed higher overwintering survival rates, and associate with that a range expansion northward and into higher elevations. So in the next slide, you will see that progression of the beetle outbreak. So you see here 97, 98, 99, it's spreading across British Columbia. It's occurring simultaneously in the United States. It's jumped the Rocky Mountains, and it's now actually approaching Saskatchewan. Now, Richard pointed out that in Canada we have a very large amount of natural disturbances, and that is largely due to fires and insects, particularly mountain pine beetle and defoliators. But you have to remember that the impact on the forest of this red blob differs greatly within regions. So, so it's important to understand that while we have large areas affected, some of these areas have only light mortality that may be 5 to 10%, moderate, severe, or very severe mortality. Of course, these are the areas down here with moderate, severe, and very severe impacts that are of greatest concerns because they have the biggest impacts on ecosystem carbon stocks. This was from a study that we had published in Nature in 2008. And so what we've done is we ran for the study area in the upper right-hand corner, which is a part of British Columbia, a scenario from 2000 to 2005 with data, and from 2005 onward using projections of the landscape carbon dynamics without the beetle. This is your baseline if you want. We then added the beetle impacts and the subsequent decision to salvage log carbon and trees that were killed by the beetle. And you can see that the impact of the beetle on the greenhouse gas balance is very large. To put this in perspective, this peak impact that occurred a few years ago is estimated at about 73 megatons of CO2. The entire greenhouse gas emissions of the province of British Columbia, which has about 3.5 million people, is about 65 million tons of CO2. So the beetle impact is greater than the human impact in all other sectors of the economy: transportation, housing, heating, etc. And this impact is the result of two simultaneously occurring processes. By killing the trees, the beetles reduce net primary productivity, they reduce the uptake of carbon from the atmosphere, and of course the killed trees will subsequently decompose and increase heterotrophic respiration. So it's the combined impact of reduced productivity and increased heterotrophic respiration that is the difference between the red and the green lines here. So let me switch to another topic, and that is fires. As you heard from Rich, fires are very important in Canada, and so what we have been doing for many years is building what we call the Canadian Wildland Fire Information System and the Fire Mars system, and it's basically comprised of many different components. We have an operational monitoring of daily hotspots. Twice a day, the Canadian Forest Service reports during the fire season where fires are currently burning in the country. We then use these hotspot records at the end of the year and retrieve data from Landsat and other satellite archives for the areas, or for a sample of the areas that we know have been burned. We also have provincial resource management agencies that map fires with fixed-wing aircraft or helicopters, and in some cases we use more coarser resolution data as the source of information. We have then developed what we call a national burn area composite. It is basically a compilation of activity data, fire data, from many different sources, and we then combine, using rules, for each fire event, the best available data. So, for this area here, we may have one fire that didn't get mapped, so we use a spot VGT, which is a coarse resolution satellite. We may have other fires where we have boundaries from agencies, and we may have other fires where we did detailed boundary mapping, including the islands that were not burned using Landsat data. And we might, for this scene, combine the estimate of area burned from all these sources. So the idea of a national activity data composite is that you compile data from multiple sources and come up with an agreement on what the best estimate currently available is of the impact of the activities. So here's just an example of the large fires database information for Canada. And you saw that Rich showed you earlier an age map. Well, the age map is in part derived from information such as this, because with these standard placing fires, we know the time since disturbance for these landscape areas. We also have land use change, a small amount in Canada, but still important. And so we have devised a national deforestation monitoring program. We need to find about 50,000 hectares of deforestation per year out of about 300 million hectares of forest. So as you can appreciate, it's like searching for a needle in the haystack. I won't have time to go into details of how that is done, but suffice to say it's based on a sampling-based approach for the entire country. So we then take all these data together, put them into this model that I have been describing in pieces yesterday and today. And we then, here's a paper that just came out, 2011, Global Change Biology, that summarizes a lot of this information. And we do this for Canada in a spatially referenced approach, which means we use the intersection of, in our case, provinces and terrestrial ecozones to generate these, what we call reconciliation units. Within each of these, we have the management areas. There's over 500 of these, and within each of these, we have the forest stands characterized by forest type, age, etc., so that we represent about 3 million stands for this total area. So that's an average about 100 hectares per stand, a little less than that, about 85 or so. And then we can generate at the national scale these kinds of data that basically show the sink or source of the managed forest over time and the drivers of these changes. So you see here the area harvested in the bottom of the graphs, the area affected by fires, and the area affected by insects. And so you can immediately see that for the first decade, 1990 to 2000, the forests were predominantly carbon sinks with the exception of bad fire years like 95 and 98. You also see the huge interannual variability, nearly 300 million tons of CO2 emission difference between a very low fire year and a very high fire year. That's about 40% of the total emissions from all other sectors in Canada. And you see the outbreak of the mountain pine beetle in Western Canada that I spoke about earlier that affects the carbon balance for the entire country. And now, in the second decade, forests are predominantly a source. So you see a transition from a sink to a source as a consequence of changes in disturbance regimes. Now, all these analyses were done using a spatially referenced approach. So the information on disturbances, on fire, on harvesting is referenced to each of the 500 spatial units. We can also conduct runs at smaller spatial scales that are spatially explicit. In this example, using 30-meter resolution Landsat pixels, this is a time series of analyses from 1990 to 1999 of an area in central British Columbia let's just zoom into this area so we can explain it a little bit better. And what you see is that from Landsat information, we identify where the harvesting occurs, which cut blocks were cut when, which other disturbances occurred, and then each of these pixels now is represented by one of these curves that Richard showed you, where we have an initial carbon content, we have a disturbance, and we have a recovery. And what you see here is the, just as an example, net primary productivity of these forests as they are affected by gradual harvesting, or by clear-cut logging, or by other disturbances. We have just run a similar analysis for a Landsat scene in Kashil-Kiwik using 20 years of data and a similar approach at 30-meter resolution. So the last point I want to make is, as one of the lessons learned, and I already spoke about this a few minutes ago, the importance of national activity data composites. You will have already seen that there are data forthcoming from a number of different agencies, nationally and internationally, that are starting to report on rates of deforestation, on rates of fires, hurricanes, etc. in Mexico. And the challenge that we face today is that we have incomplete data. But the challenge that we will face tomorrow, or in the near future, is that we will have conflicting estimates of the rates of disturbances. You just saw that Matt Hansen produced a global product at 30-meter resolution. There are other products that are being prepared. There are domestic products that are being prepared, derived by different agencies. And the problem that we will face collectively is that we do not know whether that product delivered by person A, B, or C is superior. Each of these will have some advantages methodologically, technically, scientifically, or because of local expertise, but they will not necessarily agree with each other. Now, the people who produce MRV systems and national greenhouse gas inventories are inventory compilers. They're not necessarily experts in remote sensing, they're not necessarily experts in disturbances, they're not necessarily experts in ecosystem dynamics. That means they need help in understanding which of the many different estimates of deforestation or fires for Mexico is the best possible data set. We have therefore for some time been suggesting that what needs to be done is that we develop national activity data composites. Just like in Canada we do this for insects or for fires, I think we will in Mexico need to develop a process by which we can collectively agree that for the purpose of MRV systems, Pete's source of data or Piedro's source of data or Maria's source of data is the appropriate description of this disturbance type in this region. You know, what consensus approach we use, what tests we use to define what the best data are is to be determined. But once we have these data from many sources compiled into a national activity data composite, then that can become the source of information for MRV systems, for models, and for many other users. So in summary, carbon budget models like the one that Richard described or the one that I described are essential tools to integrate data from many sources to estimate emissions and removals of both CO2 and non-CO2 greenhouse gas emissions. As I said yesterday, the IPCC encourages people to start using the best available data to identify, quantify, and reduce uncertainties as far as is practicable. And that means that the complexity of the analyses that we use can evolve over time as the data improve. Models help us in this process by structuring the analyses, by identifying available data and data gaps, and to help us in prioritizing the data collection efforts because we can demonstrate with models which uncertainties are contributing the most to the uncertainty in greenhouse gas emissions and removal estimates. National activity data composites would be useful to reconcile data from multiple sources. And lastly, because we're trying to do more than to report on past greenhouse gas emissions, but also to make projections and develop future scenarios for mitigation analyses. Models too can help us in that process. Lastly, I want to point you to the website where a lot of the publications that I spoke about are available, and I have on the last slide a list of the recent publications that deal with some of these issues that I've just spoken about, and Marcela will have all these presentations and that can be made available to you. So thank you very much.
Secretaría de Medio Ambiente y Recursos Naturales.